Okay, I think this is working. Good morning, everyone, and welcome to the second to last class of software security. For the last two parts, we're going to discuss two different case studies where we're talking a bit about threat modeling and individual issues that you can run into when working with different parts. Today, we're going to talk about the web. And next week, we'll actually look into mobile computing. They're a bit similar, but also particular. And there have been interesting issues in software security over the last 10, 20 years in these two areas. The web is special because it is really, really exposed and attackers have direct access to it. So the attacker doesn't need to be local. The attacker can be anywhere in the world and have connectivity to your services. So web services are an interesting challenge to actually secure and have been somewhat an issue over the many last years. There's two different views about the web and the internet. And one of them is that any web service is just a very long running program as network IO, as in a server. And the other one is it's a complex application with many different layers and components that are interacting with each other. So in the software security view, we have this many different layers and different alternate aspects that we need to take care of. So we can apply regular software security principles to guard the daemon by itself, right? So we can search for bugs through fuzzing. We can apply mitigations. We can enforce basic software security principles such as compartmentalization, isolation, and whatnot to make sure that these are well guarded. But then we have to protect the application in itself as well. And for that, we need to rethink exposure and different threats for web services. And this is what OWASP actually does. And we'll talk about the two sides first, the applying software security principles and then rethinking the exposure and the different threats along OWASP. And I think you'll have all heard of OWASP before as part of the information security and privacy class. But today we're going to dive a little bit deeper into the different OWASP principles as well to go separate them between each other and maybe like get into a bit more detail of some of them that are more related to the software security principles. So daemons or services or servers are the programs that provide access to different kind of internet services, right? And it's a daemon is just a long-running service that serves outside requests. Right, so a web server is a daemon as a process that listens on a network port that allows outside interaction and serves individual requests. So this can be a web server, a mail server, a DNS server, or whatnot. Likely on your computer, if you're running a Linux machine, you may be running an SSH server, a print server, your graphical user interface is running a server, Wayland if you're running a modern machine, or XLM if you're running an older machines. These are all servers that are listening for outside requests. And what makes daemons prone to attacks, right? So daemons are usually long running, right? They are complex. They're often multi-threaded. There's different levels of cachings. There's very broad, very diverse functionalities, and daemons are also exposed. So let's break this into the individual parts and talk about the subsets of these issues that make them so prone to attacks. Well, daemons are long running, okay? You start the daemon and then you let it run for forever. Now, if you think about mitigations, some of the mitigations that we have discussed, such as ASLR and stack canaries, are probabilistic. Right, so the first time you start a process, all the different memory regions are shuffled, laid out in memory and whatnot. The stack canary is set for each individual thread. Now, all of these issues, all of these mitigations are probabilistic. Is there a question?
Par contre, j'ai pas de son. Let's go, let's go, let's go.
Okay. So all of them are laid out in memory. Andres, can you mute folks? Let me see. Mute. Okay. So ASLR and secondary are probabilistic. There's got single secrets per process. And the issue with long-running daemons is that all of these mitigations that rely on information hiding can leak information, right? And an attacker may have an opportunity to run several attacks against a daemon. For example, if you're attacking a web server, you can first leak the different secret data, such as where in the address space the different libraries are laid out, how they are laid out, and then build the attack in a later step. So the attacker has multiple steps to launch the attack. The heap layout can be influenced by concurrent allocations, right? So the attacker may be able to issue multiple requests in parallel that are then laid out in a way so that the different objects are next to each other, controlled by the attacker, allowing them to set up the individual stepping stones. And like the most common part is like all of these information leaks become much more dangerous as the attacker can run the attack in multiple steps and go ahead and, after collecting all the information, actually exploit it and then go ahead and take over the server. Daemons are also complex, right? As a software resilience principle, crashing threads are often restarted. So if you look at the configuration of, let's say, Apache, right? Apache runs multiple threads per process. Usually it's around 8-ish, depending on your default configuration. And if one of the threads crashes or seg faults, then it is just being restarted, right? This is just assuming that you want to keep, you want to be resilient against crashes, and you want to make sure that you can serve requests. Now, restarting crashing threads gives the attacker the ability to leak information. For example, if you have a bug in some code that results in a segmentation fault, the attacker can use this bug multiple times to probe your address space and then see where individual bits and pieces are, right? So the attacker can probe and try different address configurations, loading different memory addresses one after the other to figure out where in the address space an individual library lies. And the crashing threads are somewhat of an oracle. The attacker continues trying until it actually works, right? So this is an opportunity. And sure, the Apache daemon could listen if I crash more than 100 times, 1,000 times, 10,000 times in a given amount of time, then it could terminate, but this is not necessarily being done. And this is usually not being done just to make sure that, yeah, well, we'll just restart it to limit the complexity. Also, daemons often have a large amount of complexity and functionality that increases the attack surface. While the configuration may limit the different code areas and functionalities that can be reached through bugs in the code, some of the other functionalities are passively reachable as well. And this may just allow multiple gadgets or different opportunities for the attacker. And CFI enables the whole configuration, right? CFI is the target sets are constructed statically, whereas the configuration is a runtime configuration, and functionalities may be disabled using the configuration, but the CFI mitigation will still be done statically on all of the configuration, all of the settings. And last but not least, there's going to be shared secrets across users in a single address space. So for example, as a web server, you're serving requests of many different users across a single address space, right? So you've got multiple people logged in on the server, and inside a single process, you are combining information from different users. So think about I don't know, a banking web application, right? There's going to be multiple users logged in at the same time inside a single address space. And just from a security principle, you would want that each user gets its own instance of the process. But on the web server, this is just being handled by the same server, handling all of these different requests in parallel and passing on the information like that. Servers and daemons are exposed. They serve concurrent users in the same address space, sharing information in the same address space, both for...
Hello?
Yeah?
Okay, no, there's a student that asked when are random things such as stack canaries, XLR updated with daemons. So.
When are random things such as stack canaries, ASLR updated with daemons? Whenever they start, right? Whenever you restart your daemon, whenever you restart your service, right? So this is an actual thread. Oftentimes there's months that pass between restarting a server. So the stack canaries and ASLR layouts are only updated whenever you restart the server or your actual processes, which can be extremely rare. Right? So it depends on your update strategy or on the system's update strategy. And let me tell you about update strategies. Most companies don't have update strategies, right? So only when there's a very severe vulnerability, they will actually update their system and restart the services. There's another question: can things like CGI help by spawning a process per request? Sure, CGI could help. For those that don't know CGI, this is like an interface that allows you to launch individual programs to handle different requests. And they usually, like the web server collects the information for the CGI process and then launches this the CGI process and allows it to handle the request inside the process itself. So this would allow you to isolate and contain the bug in the CGI process. Now, the issue with CGI is that it's like crazy slow. And the reason why servers handle multiple requests inside the same process is because it is fast, right? So yes, CGI could help, but if you look at PHP or other configurations, right, you don't want to restart the PHP engine every single time. So PHP starts caching the different results, and PHP starts caching the different files and runs them in the same process. So you can reduce the overhead of restarting and creating new processes and such. So yes, in theory, CGI could help. In theory, you could isolate and start a new process for each user request, but this would just slow things down and result in quite a bit of overhead. So in the end, it's just faster and better for your resources to limit these, to limit or to run multiple user requests in the same address space. And yeah, outside connections are allowed, right? So the attacker can be anywhere. The attacker can request information. The attacker can interact with your service. And oftentimes there's multiple levels, right? The web server is not just serving static HTML pages in most cases, but there's administrative interfaces. There's special pages only visible to the user itself, to the user that is logged in, right? So there's going to be the same exposed interface to both not anyone on the internet, logged in users, and an administrative interface as well. And the only difference between these different different users or different user levels is who is logged in or not, and a little bit of data that's being sent back and forth. But the code running for all the different types is the same code, right? So a bug in the regular outside, not logged in user interface could be used to compromise logged in users as well. And you can spill between each others. And then attackers can leverage many diverse and different IPs, right? So the attack doesn't need to come from one single place, but can come from many different places. Now, in this environment, how would we ensure that like an attacker cannot just run tens of thousands of different requests? Now, rate limiting accounts is incredibly hard. There's we could tie the number of connections to logged in users, but then we would have to keep track somewhere globally who is logged in at any given point in time, who is interacting with the server, and then keeping some kind of count. And this is a trade-off between like limiting functionality or benign functionality and limiting attackers. So I don't know if you've ever tried downloading a lot of pages from Google or some other pages. They may rate limit you at one point in time, right, if you're scripting it. But they are locking this on a per IP basis. If the number of requests from a given IP is too high, they will try to rate limit you and like, I don't know, show you captchas or whatnot to limit the amount of interactions. But attackers can still use multiple IPs and multiple different networks or multiple compromised hosts or whatnot. So this is a partial solution that will limit an attacker from one single machine, but there's always ways around it. Sure, you could require access tokens with each request and such, but this may also be challenging because attackers can just create the different access tokens. One interesting aspect that I've seen in CTFs being used is that for each request that you are issuing, you need to do a proof of work. Which is, for example, if you're interacting with a challenge binary in a capture flag that is hosted online, oftentimes you have to solve like a hash challenge first. That you need to find a hash collision where a certain amount of bits is the same, right? So you need to run a proof of work and then have a hash collision, create a hash collision with a certain amount of bits on your system, and then submit this proof of work to then actually have the server do some heavy work, right? And this limits the amount of interactions that you can do in parallel. So thanks for sharing the link, Lucas. Yeah, this is exactly what I was talking about with this proof of work. So yeah, it's a way to limit individual IPs, but an attacker that controls a botnet can still run many of these requests in parallel by solving and just using compute resources on the attack on their compromised machines. How do we protect daemons and services? Well, compartmentalization is one aspect. We can break the complexity into smaller components. We can develop fault compartments that then fail independently. And the goal here is, like, if one component fails, others will continue to function. This is just applying regular software security principles to it. Compartmentalization is key. It may be challenging to design, especially for web applications. So you could forward requests of logged-in users to another domain by allowing them to hop over to a different server, or just compartmentalizing these privileged information on a different server as well, right? But it's very, very challenging to design. It's very challenging to handle. Still, applying best practices in software security makes a lot of sense and should be done on these systems to just like have a baseline of security. Apply mitigations if you can, enforce mitigations such as control flow integrity on the configuration itself. So as in limit functionality at compile time. So you can remove, in many configurations, you can remove the unneeded functionality with compile time flags, and this will then improve different kind of defenses like control flow integrity alongside. If you've ever compiled, I don't know, Apache, the Apache web server on your own, you can select which kind of additional features you want. And to empower control flow integrity and other mitigations to their fullest, you want to limit the amount of included options and included services. So if you don't need an old style CGI interface, you can disable it at compile time and not even compile this functionality. If you don't need obscure cryptographic ciphers, you can disable them when compiling OpenSSL, right? So that you have a bare bones limited configuration that allows you to protect the system at its strongest potentials and enable mitigations to be as strong as possible. Questions about applying software security principles for to web services? Are there any questions? Okay, if not, I'll move over to OWASP. Move this window. So OWASP is the Open Web Application Security Project, and it collects information about threats, about attacks, and about different kind of issues that are happening on the web, and they're trying to come up with a ranking that allows people to train and be aware of these different kind of issues. I assume you have heard of OWASP, at least in some of the other classes. Now we're going to talk about some of the top 10 list in a bit more detail and go through the top 10 list really through some of them rather quick, but some of them in a bit more detail. If you haven't heard about the OWASP, it's a framework or an entity, to say that just collects information about different kind of attacks on the internet. And they collect details about how different web applications are being compromised. So they collect information about vulnerabilities, attack vectors, ways how users are attacking them, ways how if the configuration is okay, if different things are being compromised, updated, modified, whatnot. It's being updated periodically, so you can check out the top 10 on owasp.org, project top 10, and they will update it every now and then. Previous versions were in 2013 and 2017, and towards the end we'll also discuss how the different attack vectors evolved over time. So the top 10 are as follows, right? Broken access control, cryptographic failures, different kinds of code injection, insecure design, security misconfiguration, vulnerable and outdated components, identification and authentication failures, and software and data integrity failures. Security logging and monitoring failures, and server-side request forgery, which is new this year. We'll now go through this top 10 and talk about them from a software security perspective for a bit. If there's any questions for any of them, just let me know. In the ISP course, how deeply did you discuss the OWASP top 10? Just a brief overview. Yeah, that's what I figured. So we'll do another brief overview, but we'll talk about it from a software security perspective, right? So there could be its own class about web web application failures. We don't have time for a full class on this because it's a there's just like one case study. So we'll look at it from a software security perspective and then go into it. If you're interested, there's a lot of good training material online on the OWASP website. So if you wanna know more about web security, we unfortunately don't have a class about it, but there's all this training material that you can refer to and then go deeper. It's at the website that I mentioned. So the very first one, broken access control. Is this working? No, just close the chat. No, I'll move it here. Broken access control, which restricts what authenticated users are allowed to do. These restrictions are often not properly enforced, right? So access control manages what different users that are logged in, not logged in, have privileges or whatnot can do. And access control is often faulty or missing or incomplete. So web applications implement access control checks in a somewhat haphazard way, and this could lead to unauthenticated users or authenticated users of lower privileges to access different kind of files in unintended ways. Attackers can exploit these flaws to access different kind of functionality and data, such as other users' accounts. Remember, this is all running on the same system, right? The process is running as the web service, right? If you run as a difference, right? If you're logged in on your system and you're running a program, you're running the program under your user. If you're logging into a web service, the web servers will run as the web service user, right? So there's one web service user, and all users logged into a web service, into a daemon, are running with the same user account. And there's no distinction between user 1 and user 2. It's all running as the web user service. So if there's a bug in the access control logic of the web application, user 1 can simply access the data of user 2. There could be issues of viewing sensitive file, modify other users' data, change access rights, and so on, right? Examples of missing access control are different forms of unprotected access to the admin interface, different access to backend services such as storage, FTP, and so on, and access to database interfaces, backend services, different kind of private REST APIs that controls local information or whatnot, right? So this is all possible, possibly exposed. The ways to protect broken access control are like, except for any kind of public resources, you can have a deny list at the web server itself and just deny access to non-public resources by default to make sure that you don't have an allow list, but an actual deny list. You can limit exposure. So you reduce log information to error code. So as in, like if there's an issue accessing a resource, instead of giving a complete stack trace, you just give an error number to the user and you log all the information to a dedicated log that the developer can then look into. So for example, if a web application crashes, you as the user, I'm sure you've seen this on the internet, you may get a full stack trace of where the bug actually happened. And you may not want to expose this to the attacker. You want to disable directory listings, right? If there's if you access a directory, you could leak a lot of information there. You want to rely on central access controls, rate limit different kind of API calls, especially to expensive services, enforce access checks at these kind of interactions, log access control failures, and then actually check the logs in addition to that. Logging is good, actually checking the logs is better, right? So you need to do both to detect an attack. And then limit the amount of damage that an attacker can do by enforcing some form of compartmentalization on the different services. And interestingly, over the last couple of years, broken access control has moved up and up and up. And this is now the top one threat of OWASP applications, right? So this is the most common issue that web applications have in this ranking. So broken access control is the key issue that we are facing with web applications. So be sure to take special care and actually write down what the access control is and how this is being handled in your application if you ever develop a web application. Number 2 is cryptographic failures. This has been renamed in the most recent version. And the issue is that many web applications and APIs do not properly protect sensitive data, such as financial data, healthcare data, and PII, personal identifiable informations. Attackers may steal, modify weakly protected data, and sensitive data may be compromised without these extra protections, such as encryption at restaurant transit. And most of these issues are that, for example, user data is not stored correctly, right? You may store a password just as plain text in the database, and you should not store a password as plain text. You should store the hash, right? If you have personal identifiable information, you want to limit the if you have personal identifiable information, you want to limit the amount of damage that can be done in the system to so that the attacker can only leak the encrypted version, and the attacker would have to steal both the encrypted information and the key to decrypt it. Similar to rate limiting with access control, this is an option of providing defense in depth. Right, so there was just a question in the chat, why does rate limiting help with access control? It's the same as why does encryption help with protecting data? An attacker needs to compromise multiple things, right? Rate limiting allows you to, assuming there are bugs, allow you to detect and react to ongoing attacks and limit the amount of damage that can be done. Similarly, if the attacker needs to steal a key along with data, the attacker needs to first steal the data and then figure out where the key is to then make use of the underlying data. So this is like a defense in depth, second layer. Why is personal and sensitive data so hard to protect? Well, personal data, similar to biometric information that we had discussed very early in the class, are very hard or pretty much impossible to change. You cannot change your fingerprint. You cannot change your iris. I don't know if you ever had to go through this, but renewing a credit card, if there's been credit card fraud, it's very annoying. But changing your name or birth data is not something that many people want to do. And changing your fingerprint is just simply biologically not possible. So exposure of such information, like records with names, emails, birth dates, fingerprint information, password, and so on, this cannot really be undone. When the information is public, then it's game over. So you cannot recover from it. You cannot just restart the service. You cannot just rehash the service and launch with a different ASLR setting, right? The information is gone, and protecting the identity of individuals is extremely challenging, right? So we need to make sure that the information is not being lost in the first place, as recovering from a loss of information is extremely expensive and takes a lot of time and effort. Unfortunately, sensitive data is frequently exposed. And this is partially a result of business strategies to store as much data as possible, under the assumption that it may be reused later. So you may have seen that a lot of companies are collecting as much information as they can, right? So they are, whatever you're entering, whatever your you're storing. The companies will keep a log of all of your private interactions forever. They will keep a log of all your chat information. They will keep a log of all your emails. They will keep a log of all your pictures. They will keep a log of wherever you click on a website, how you move your mouse and whatnot, under the assumption that they can later use this information to mine additional information, figure out profiles, and then show you ads about your behavior to make you buy more things, right? This is how the business strategy of the web actually works. And this is why all of these companies like Google, Facebook, and so on, or even newspapers or whatnot, collect all this information. When data is stored for later processing, similar to debug information, data leakage may result in a full loss of all data. So this is why you should design systems as if you're following security principles, that only stores the bare minimum of data that is actually required for your processing, required for your tasks. The goal is to store and process minimum amount of sensitive data and directly throw away as much sensitive data as you can. Separate and aggregate them into compartments, and then create data policies that record where and how and what data is being processed, so you can actually differentiate between different parts. And if or when an attack actually happens, you can go back and figure out what the different issues were to limit these kind of things and recover from compromises. Because assuming a compromise will happen allows you to have a strategy to recover from it. Similar to software security principles, right? We apply software testing principles to find and remove as many bugs as possible. Then, in addition, we use mitigations to make it as hard as possible. And then we use compartmentalization and other strategies to limit the amount of exposure that happens if an attack is actually successful along all of these different steps. And then as a fourth place, we need to have strategies to recover from attacks after they have happened. Right? So we need the similar principles for sensitive data, right? First, we want to figure out the minimum of data that is being necessary. Then we need to store it in a specific way to detect how it is being accessed. And if it is being leaked, we want to limit and detect what kind of leakage has happened and then react to it in a good way. So protective data, sensitive data is essential for web applications. You need to be aware what data types are being handled. So you need to actually record this in your threat modeling. Only store whatever is needed, nothing more. And then protecting data at rest and in transit. So for example, if there's user data, you need to encrypt it. And only store, for example, password hashes. And the password hashes are actually the most common issue that are happening, right? So you need to make sure that you're not storing passwords in plain text. This seems to be the most common issue, and it's surprisingly common, right? So this is the second most common issue in web applications. Top 3. Let's move on to the next one. And I think this is the most fun for us because it's code injection, and there's 3 types of code injections that we'll talk about here that are very, very similar to code injection or code execution in just regular applications, but just like twisted towards web applications. And there's injection flaws such as SQL, NoSQL, OS, and LDAP injection. They occur when untrusted data is sent to an interpreter as part of a command or query, right? So you're sending a request to the web service, and then the web service actually handles it. The attacker's hostile data can trick the interpreter into executing unintended commands or accessing data without proper authorization. So there's a lack of split between code and data, and some of the data may be interpreted as code. This is like a typical code injection attack that we already know from like the beginning of the class. Code is not restricted to executable instructions, right? This is the big difference here. Web applications execute all different kinds of code, which can be under the control of the attacker. So command injection and SQL injection are two prime examples, and cross-site scripting is the other big elephant in the room. The code injection part, this is a code injection or command injection, is a unfortunately very common approach. A very common issue. The Unix philosophy is that we want to leverage simple tools to achieve complex results. So this is the core philosophy of Unix systems. And you may be reusing different kind of scripts or programs and pass different data as parameters to them. So for example, your Wi-Fi router at home may have different utilities to in the web interface. You may, I don't know, change the IP configuration of the router, ping other programs and whatnot, trace routes, change things. And for many of these options, right, it is not implementing all of this functionality in the web server binary itself, but it is simply collecting the information from the web interface, then exec calling a shell and passing this information to the shell. This constrained communication channel contains both code and data, the query command and the query arguments, and then you're just launching this in the web application. While functionality is tested, the security guarantees are often not, right? So you need to make sure that this actually, you cannot escape this limited shell. And so you need to make sure that all your arguments are correctly escaped, embedded, and made sure that they are not, cannot be exposed or leaked. So these dynamic web pages execute code on the server, and this allows the web server to add content from these other sources, for example, databases and whatnot, or the result from the ping command, as I mentioned on the Wi-Fi router. So these complex queries are being built dynamically, and then the final result is then sent to the user as a content management system or whatnot, which includes data from the database, site templates, navigation modules, and whatnot. So command injection may look like this, right? So your Wi-Fi router may have a display a file kind of functionality, and in PHP you may just write echo system cat the file that you can include, and this will nicely include a file, right? It sounds simple. But you're actually launching a shell. You're actually passing this information to a shell, and in the shell you're executing cat my file. And this can result in many different kind of issues, as there's no separation of code and data. So you can an attacker could pass this information, display file equals x.txt, and then semicolon cat etc password. Right, so it allows a chaining of individual the semicolon, which is OX3B as an ASCII character number, allows chaining of multiple individual bash commands. And the system function is like a very powerful command that executes full shell scripts. And of course, there can be multiple commands that are being chained. And this results in these kind of issues. So what are reasonable mitigations? Can you just block semicolon and grep for semicolon, have a regular expression and remove it? Well, we could, but blacklisting or deny listing is not a good solution. So the attack space may be very large. What about using a pipe? What about using a backtick? What about other commands, cat instead of remove? What about different kind of built-in commands that are in the shell itself? Right, there's a lot of functionality that with just deny listing you have very limited control of, and you need to make sure that you can cover all of that. So deny listing is not a good option. What are reasonable mitigations? Well, first you can do validation. you can check against an allow list. Ensure that the file name matches a set of allowed file names that you want to concatenate. Whenever you want to execute commands, you need some form of non-alphanumeric characters. So you can limit the string that is being passed. You can hard code directories, you can set allowed files, you can disallow special characters in the file. So you can check all of these different parts. You can validate that the command is actually correct or that the arguments are being correct when you concatenate them. You can escape them, right? That's the second mitigation. So you can escape parameters so that the interpreter can distinguish between data and control, right? Because all of the arguments that you want to pass are simple data. So you want to make sure that the arguments are actually correct and cannot be escaped and turned into data. So an escaped form may actually be system, open parentheses, double quote, cat, single quote, file.txt, single quote, end quote. Now the question is, how do you write such an escape function? Right, you need to carefully design the escape function and make sure that you're handling all the different cases. But you should not be writing your custom escape functions. This is also a common issue that a lot of people do. They just think, oh, I'll just write my escape function myself. It's going to be easy. I'll just add the checks and quotes and whatnot, and I'll be done. Unfortunately, this doesn't really work because there's a very high likelihood that you'll forget one thing or another thing, right? It's quite challenging to actually do so. And each language has its own flavors of issues, and people that spend quite a bit of time thinking about these kind of issues have then designed escape functions. So do check what kind of escape functions your web framework has. For example, WordPress has different kind of escape functions. Other frameworks have other types of escape functions. So make sure to use those and figure out what the best function is for that. And don't write your own. It's similar to cryptographic primitives, right? The most important lesson about crypto protocols is don't write your own crypto functions, right? Just reuse the existing functions out there and figure out what the best existing function is that you can use. Never implement your own crypto protocols or whatnot. Last but not least, like you can mitigate command injections through a reduction of privileges, right? So the system command is simply too powerful as it launches a new shell interpreter. For most cases, you don't need a system, the system function. Limit yourself to the simplest possible API. Open the file, read it into a buffer, or if you must execute a command, launch it directly and not through the shell itself. So just launch the command and don't start a shell that you didn't pass data in. For PHP, you can just use file get contents, which is much simpler and doesn't run and launch a full process in the interpreter and whatnot, right? So you can actually limit the amount of privileges that are being used. So what enables these kind of injection attacks when we generalize code injection attacks? The issue here is that both code and data share the same channel, right? We are trying to pass a parameter to a function. We are trying to pass a parameter to a shell command like cat file name. So the cat should be specified. The cat is the program that we want to run, and the file name is information that we want to pass. But when we launch it, the issue was that code and data share the same channel. They are encoded in the same string. The cat and the file are specified as part of the same shell script. And here the issue was that the semicolon starts a new command. And in all these different code injection attacks, the data and the stack, the executed code share the same channel, right? So in code injection, we've seen it's similar. The code or the data on the stack can be interpreted as code. And if you get execution or the CPU to execute or point instruction pointers to the stack buffer, then it may just be executing these injected instructions, as do like the code pointers. And with SQL injection, it's actually quite similar. Here we have an example of SQL injection. Select all from users where emails equals parentheses get email and password equals like a quote the password. And here the get command just simply uses the data that is being passed into it. Right, this is exactly the same. We are concatenating, we're creating a string and concatenating different parts from a program, which is to select star from users where email equals and pass equals. So that's the program, and then we are adding some data to it. So we're getting email and we're getting the password variables from that are specified by the attacker, and we're just concatenating a new string together. And an attacker may inject or pass an email that contains a quote character to escape queries and then be able to inject their own commands. As a second issue, the password is stored in plain text, which should not happen. So you should be able to hash it. And SQL injection is in spirit pretty much the same attack as code injection or command injection that we've already seen. Right, so we are passing information that is controlled by the attacker directly into our process, where it is supposed to be data, but it could be misinterpreted by the program or by the web application as code, and thereby executed. So we don't want to execute attacker-controlled data as code. So to mitigate SQL injection, we can do validation, similar to command injection, escaping, similar to command injection, or reduction of privileges, similar to command injection. The simplest form is to use separate control and data channels, which is the straightforward mitigation for SQL injection. So we can do prepared SQL statements. So similar to printf, we can define a format string and then later supply the arguments. So this fundamentally gets rid of SQL injection itself. So we define the code, select star asterisk or select all from users where email equals first parameter and password equals second parameter. And then we supply the email and password commands to this SQL, to this actual prepared statement. And then we don't need to worry about the information that's actually being provided. And this separates the control and data channels from each other and allows us to actually provide the information as intended and required. So how do we prevent code injection? Well, we can use a safe API, as in the prepared statements in SQL, or restricted commands for shell commands. We can validate inputs based on an allow list. We can reject invalid inputs. And for any remaining dynamic query data, we can escape the commands using a variable, right? We can escape commands using the available API. So don't roll your own escape functions. If you need an escape function, do check what kind of escape functions the system actually provides and then use those. And then you can limit code injection vulnerabilities in your application and limit one of the top 3 issues that are happening in web applications. Now, the third option of command injection or code injection is cross-site scripting. And so cross-site scripting allows an attacker to inject and execute JavaScript or other kind of dynamic content in the context of another web page. So for example, malicious JavaScript code may be injected into a banking app, of a user to extract username and password, or to like issue and start counterfeit transactions. There's 3 types of cross-site scripting: persistent or stored XSS, reflected XSS, and client-side cross-site scripting. And the idea is that you have your web page and you're executing attacker-controlled, or the attacker is executing JavaScript that they control in the context of your web page, and thereby extracting information or extracting additional details that they should not be able to extract. So the attacker stores for persistent cross-site scripting, the attacker stores the attack data on the server itself. And let's assume we design a simple chat application, which allows the users to store arbitrary text that is then displayed to other logged-in users, right? The attacker may send a message that contains script alert, Mr. Evil is here, end script. Now, if the web server simply stores this chat message and appends it to the file, as in, or to the database or whatnot, and then other users browse to that page, they will execute this script in the context of the web application and of the context of that user, right? So the attacker sends a chat message, script alert, Mr. Evil is here. It is being stored on the server side, and then all the other users that access this page download this script and will execute it on their end. And here the bug is on the server side, because it allows the attacker to store this script information in the database or file or whatnot, and then distribute it to the other users. The bug is on the server side and needs to be fixed by ensuring that an attacker or a user cannot store script information that's then being executed and included verbatim. Reflected cross-site scripting is another issue. Another form of cross-site scripting. The attacker encodes the attack data in the link that is then sent to the user. So for example, through an email or a compromised site. A web interface may return your query as part of the results. For example, you can encode a query that will pass like a search string to Google, right? So you can do www.google.com/?q for query equals the word that you're searching for, right? And then Google will tell you, oh, you have searched for query, right? And this returns 23 results. Now, if they don't check the query that you're sending, and your query includes some form of script or JavaScript, this may be executed in the context of the user itself. The issue here is, again, that the bug is on the server side, because the server script does not check what kind of data is being included, and simply returns the data that is being passed. Now, the requirement here is a little bit different, because the user needs to click on this attacker-controlled link to actually execute the attack. It's not included by default. So it's a little bit harder to pull off reflected cross-site scripting, but it's much easier to control, right? So here the attacker prepares a malicious link and then sends it to the user, and the user needs to click on the link. Whereas with persistent cross-site scripting, the attacker simply stored the data on the server side, and simply a user simply browsing to the website already launched the attack. Client-side cross-site scripting is a bit more complicated, and has recently become an issue as well. So large applications contain lots and lots of JavaScript code, and code itself may contain vulnerabilities. So the JavaScript code on the client side may use different kind of URL parameters to process information, Think about like JSON requests to process data in the background. And the attacker makes the user follow the compromised link, but then compared to reflected cross-site scripting, the server does not embed the JavaScript code into the page through server-side processing, but the user-side JavaScript parses the parameters and then misses the attack, right? So the attacker is providing this JSON request data, and the client side is missing the validation, and therefore the cross-site scripting code is being executed on the client side. So the bug is on the client side here by client-side JavaScript code that processes attacker-controlled data and does not manage to escape it. Think about Gmail, right? An example would be Gmail, where the client-side code downloads an email that is being controlled by the attacker, and the email contains JavaScript code, and the client side needs to make sure that this JavaScript code is not executed as code, but simply displayed as text. All right, so this would be an example of a potential client-side cross-site scripting issue. Now, mitigating cross-site scripting, again, similar to the other issues that we saw before, you need to properly escape input. And again, each framework has its different subtleties. So you need to make sure that you use the correct escape functions for that. Use the provided escape functionality in your web framework and review the code that this actually works out well. So you can detect data flow where unfiltered input exists. There's papers on this, and yeah, different kind of code reviewing of your application will make sure that this doesn't really happen in practice. And to summarize all these different types of code injection, you need to separate data from the web application logic. You need to isolate this. I need to make sure that you can actually, separate the code from the data, prepare statements, limit different kind of the data exposure and access. So one database user for access, another one for admin as an isolation principle, and then use safe API functions and validate based on different kind of allow lists instead of doing this in an unsafe manner. And yeah, just follow best practices to enforce these kind of separation issues, and just be aware of this attack vector. So this is the third most common attack vector. It used to be the top most common attack vector. As people have become more aware of code injection, they are starting to use different mitigation techniques such as vetting and checking and so on. This is making this a little bit easier and better, but it's still a very, very common threat vector. Questions about code injection attacks? Okay, let's continue. Insecure design. There's a this is a new threat, and it has entered at the top 4. So this has become quite important, but it's a kind of a fuzzy catch-all part, right? So this catches everything that is not really fit for another category. So it covers different kinds of abstract issues, such as lack of threat modeling, like in not having an explicit list of threats for your web application, lack of focus on secure design patterns and principles, and it's like anything that is, that part of the design of the application. So it catches any kind of faults that are not really a fit for all of the other categories. And it allows you to discuss these kind of trade-offs and aspects. It's mostly in the design phase. That's why it's called insecure design. And then you can, by doing a correct threat modeling, explicitly writing down the design, following good design patterns, code principles, and so on, you can mitigate this issue. So this one was new for 2021 and hasn't existed before, because people observed that more and more such attacks are actually happening. And yeah, there was no good auto category for this, so that's why they added it. Security misconfiguration. That's another issue, right? Oftentimes, when you're working with web applications, you'll be tweaking and tuning and changing things a little bit until it works, right? So this is an iterative approach, and when it works, you're not sure if it is working as intended or if you have added any kind of issues on top of it, or any kind of if you've opened up any kind of threats, or if you've enabled debug mode or whatnot. And security misconfiguration is the result of insecure default configuration, incomplete or ad hoc configuration, misconfigurations, whatnot, error messages containing sensitive information, and so on. You must, for the web application, you must securely configure the operating system, the framework, the libraries, applications, and so on, and patched and upgraded in a timely fashion. Now, the issue here is that keeping track of all these configurations across all these different layers is incredibly challenging, because the different layers may interact with each other. And it's extremely easy to misconfigure, right? If you just allow access to all the different layers, and if you just configure it to be as open as possible, it will work, right? For benign cases, it will work. But from a security perspective, you have just given access to everybody without being logged in or whatnot, right? So you need to make sure that the configuration is tight, that the configuration allows the intended functionality, but disallows any unintended functionality. And for that, you need to make sure that it's not just working, but it's also protecting access towards resources that should not be accessed. And usually the second part is being forgotten, right? To make sure that the access restrictions hold as well. So a service uses the example demonstration configuration. This can be an issue if you don't limit the amount of functionalities provided. A development configuration could be deployed in production, so it may leak detailed error traces, debug output, or other kind of unnecessary log output. Also, different kind of added components or libraries are not vetted and are not limited in how they can be used and accessed. A common security misconfiguration that used to be its own threat and its own used to have its own entry was the security the XML entities. XML used to be the language of the web, and XML processors validate and evaluate external entities when referencing them in an XML document. So they could be used to disclose internal files using the FileURI handler, internal file shares, port scanning, whatnot, and just access different kind of parts. You should not include the external or untrusted resources. You need to sanitize this use uploaded data, and maybe use simpler data formats such as JSON, which can reference other documents. So this used to be an issue, right? That in XML files, you can include other files or reference other files that then result in weird ways. The image that I'm showing here is the billion lol attacks, where there's an entity defined called lol that includes an entity lol2 that includes lol 10 times, and then lol3, which includes lol2 10 times, and so on. And here we have lols that includes lol9 that just references all the other entities, and this results in unrolling all of these previous entities and just exhausting all the server resources. So this is an interesting misconfiguration where the XML parsers should not be resolving all of these issues. XML parsers shouldn't include external files and whatnot. So you need to make sure that you can configure this correctly. How do we prevent misconfiguration? Well, we need to document the configuration that we are using, what kind of software we are looking at, what kind of configuration we are looking at. I need to keep the systems up to date. We can use compartmentalization. We can review different kind of configuration changes and whatnot, right? Yeah, and then make sure that this actually works and is done in a nice way. Now, I've just checked the time. My suggestion is that we just continue for another 15 minutes, and then we should be done, if that's okay with you. Or
okay from this side.
Okay, cool. So let's just continue. Another common threat, number 6 on the list, is vulnerable and outdated components. So using components that have bugs, and oftentimes it's fairly challenging to have all of these different components together, and the software stacks are deep and complex and so on. And you need to keep track of what libraries you're using, what frameworks you're using, what software modules you're using, which privileges they are running with, what the settings are. So this is like a multi-layered, difficult problem. You need to keep track of it, and you need to update them depending whenever vulnerabilities are being found or discovered. So you can actually keep track of the security issues. Mitigating these kind of insecure components is not too hard. Well, you can remove unused dependencies. That's the first step. And you need to document components and dependencies in the first place to be aware of what the issues are, and then just monitor for unmaintained libraries or components. Whenever there's a CVE, figure out what the issues are, where they are, and whenever a new version is available. And then install this newly added version and whatnot to make sure you can limit the impact of vulnerable components. If components are no longer updated, you can then move on to make sure and remove them and replace them with a library that actually is updated. So top 7, identification and authentication failures. This is another issue where the application functions related to authentication and session management are potentially implemented incorrectly, allowing the attacker to bypass authentication or identification, allowing them to compromise password, keys, session tokens, or whatnot. Most likely these are session tokens that then allows the attacker to reuse a token or whatnot to assume the identity of another user to escalate their privileges or access sensitive information. A multi-factor authentication mitigates these kind of brute force attacks, password leaks, and whatnot, and allows a defender to limit the impact of this kind of issue. Another approach: never use default credentials, especially for administrative interfaces, and develop a reasonable password strategies to mitigate it. You could limit or delay the amount of failed login attempts and log any login failures, and again, check these issues. These unauthenticated accesses, the most common approach is that there's a forgotten admin page. So web services often have default administration pages, such as administrator, WordPress admin, admin for index.php/admin, and whatnot. And oftentimes these are just left open and unconfigured. And if you ever run your web service or a web server and you check the log file, the most common accesses, even if you're not using WordPress, will be an access to WordPress admin that is being tried. There's bots constantly scanning the internet and trying to find these kind of issues. So whenever you set up a new WordPress instance, you need to disable this very, very quickly so that this cannot be attacked or while you're actually configuring it. Otherwise, a malicious user may access the exposed admin resource and gain full unmediated access. Secret pages do not work, so you need to make sure that they are actually protected. Attackers may guess hidden URLs. So protect all of these interfaces and make sure that they are, cannot be used by the attacker. How to prevent such kind of vulnerabilities? Well, implement second factor for everything that's important. So username and password is the first factor, and then maybe either an email login, a security token, an SMS or whatnot as a second factor to make sure that this actually is a secure device. Never deploy with default credentials. Test the registration, but not just the registration, but also password recovery, API usage, whatnot, against different kind of attacks, and review all of these different processes. At best, you will have a flow diagram of the different processes that make sure that there's no shortcut or no way for an attacker to get around it. You'll have to rate limit failed login attempts and provide a secure way to recover passwords and accounts, because that's often an issue here as well, that the password recovery process in itself is incomplete and would allow the attacker to compromise parts. There's just a question, what is the difference between broken access control and broken authentication? Broken access control means that you are user X and you should have resource to file X. I'm user Y and should have access to file Y. You as user X can access my file Y. So that's broken access control. You should not have access to my file or my data. Broken authentication means I can log in as user X while I'm just user Y. In a very simple way to distinguish. Hope that makes sense. So access control means checking what you can access as logged in user, as administrator, as regular user at the different kind of privilege levels. Authentication means I can log in as you. Does that answer your question, Philip? Cool. Top 8, one of my recent favorites is software and data integrity failures. Unfortunately, it's only top 8. I think this should be a much higher issue, and maybe we'll see that change going forward. Insecure deserialization often leads to kind of remote code execution. So web services request or get data from the attacker. So for example, when you're sending an email, for example, in Gmail, the user side or client side JavaScript part packages up the email that you're sending and sends this as a request to the server. The server takes this request, unpacks it, deserializes the data that is being sent as a blob, and then parses it and reacts on the information that is being done. This is being called pickling or unpickling, as in you're extracting data from it. And issues in the deserialization part of the server side may result in different forms of injection attacks or code execution attacks when new objects are being instantiated or whatnot. It's an extremely fun attack vector. An example of insecure deserialization is a simple cookie that contains user ID, name, role, and password hash. Right, so you may have user Alice with user ID 1000, and she has the role of admin and the hash. And Mallory has user ID 1001, is just a user and has this other password hash. So Mallory can gain admin access by simply encoding the admin field and replacing user with an admin. Other example means like you could just provide unpickling of objects, so providing an array instead of a string, which results in weird issues for Java, PHP, or Python. Unpickling different kind of unintended classes or whatnot, and this then results in different forms of code execution in the Java framework. So if your application expects a string, but the attacker is sending an array, then the equal match will potentially not work, and other kind of issues can happen. Mitigating insecure deserialization could be done through integrity checking for the cookie example, enforce type checks during deserialization, like you're only deserializing the object that you expect. You can make sure that this is a string that you're deserializing and not an array or a map. Isolate the parsing code to a deprivileged process, and then log kind of deserialization exceptions that are happening. Top 9, insufficient logging and monitoring. Well, there's the one case we already discussed was that it was too much logging, providing log information to users, but there's also the case of insufficient logging. Oftentimes, log files are just being written to the computer somewhere in a basement, and nobody looks at them. Most breaches are detected very, very late. So it takes 200+ days to detect an attack against an application. And by then, a lot of the attackers have extracted all the data they could have, actually be interested in. So as a good defensive strategy, you need to monitor the different kind of logs that are being produced by the web application, by the web server, by the daemons and whatnot, and then detect if any kind of issues are happening. So you need to log, monitor, and couple this with an effective integration into incident response that allows you to react to ongoing attacks and stop attacks before they can escalate their privileges, extract, exfiltrate data, or tamper or destroy data in other ways. An example of insufficient logging, companies often have these log analysis frameworks running in parallel that highlight way too many threats and making it hard for the companies to prioritize what is an actual threat or not. Brute forcing logins is extremely noisy, results in millions of log entries. If these log entries are not analyzed, an attacker may just gain access to the system by brute forcing, right? But there's also benign users mistyping their passwords, so there can be issues as well. So you get noise in the background, right? Because there are users that are mistyping their passwords in the first place, and you need to distinguish the noise in the background from an actual attack that is probing many different logins in parallel, right? So it's a weird trade-off that you need to look into. Ensure errors are logged and log files are evaluated based on different thresholds, and you need to prevent some form of audit trail for these important transactions. For example, whenever somebody logs in after mistyping a password a couple of times, 5, 10, 100 times or whatnot, so that you can check and maybe challenge for a second factor or whatnot. But you need to actually implement these practices because they will not be used by default. Last point, the number 10, server-side request forgery. It's an interesting point that was only added to the OWASP top 10 based on user and community feedback. So the observation here is that this may become a threat going forward, but the data does not show up in active monitoring yet. So there's very few incidents. So this has only been added because of the community feedback to this top 10 list, but the community thinks that this is an important issue going forward. And the idea of server-side request forgery is that an outside attacker tricks the server to open a request towards the internal framework. So servers are often dual hosted, right? They're part of the internal network, but they expose an interface to the external network. And the idea here is with server-side request forgery that the attacker tricks the web application to query the internal network and to expose data. So the attacker uses the application, the web application, as a confused deputy to access resources in the internal network. So for example, to forward some information to an internal web server and to include that through an XML external entity include option. This would be a prime example for server-side request forgery issue. And it's not being observed as a main threat vector now, but it's a way to get around firewalls and other kind of restrictions. And the community feedback is that this is going to be fairly important going forward. And we may see this, this more in the future. So let's look at the OWASP evolution for a bit. So if you compare the 2013 to 2017 versions, we've seen that the code injection remained as a top one priority. Broken authentication was also top two. Cross-site scripting became less important. Sensitive data exposure actually increased. In the secure object references and missing function level access restriction became access control. Security misconfiguration got less important, but then sensitive data exposure became more important, right? So these things have changed as the threats on the web actually evolve. Now, moving from 2017 to 21, we saw a much more heavy set of changes, right? First time since the OWASP was around, code injection is no longer the top one. And broken access control has actually become much more important. So from 5th place, broken access control has now moved to the first place, to the top place. Security misconfiguration has become more important as well, same as using components with known vulnerabilities from the 9th place to the 6th place. So we see an increase in that. As frameworks are getting more and more complex, it becomes harder to secure, and people forget to just update them and make sure of that this is being actually included correctly. Most interestingly for me is that code injection and cross-site scripting have been merged, and that it dropped 3 places, now being much lower than before. But yeah, this is just OWASP observes the attacks over several years and then updates their top 10 based on the number of incidents, their impact, their threat level, and so on. So this is an interesting way to see how attacks shape and evolve over time. As a summary, well, there's code injection, broken authentication, data exposure, and so on, that are threats to different web applications that you'll be working with or maybe even programming in the future. And interesting, if I try to summarize this, the different threats, parsing is extremely challenging, and you need to take care of input parsing. There's code injection, external entities, cross-site scripting that all result in different kind of code injection opportunities for an attacker that makes this extremely difficult to work with, right? So we need to be aware of injection opportunities and need to protect and secure the parsing of web applications. This is true for regular software applications, regular binary applications, but also for web applications. This is a very common threat that is just a part of a software security life cycle. Second part is authorization. The issue here is, and this is different from regular applications, where regular application will run as its own user. In a web application, you need to make sure that you are acting on behalf of the correct users. You don't have the operating system that tells you, hey, you can't access that file. you're not the right user. You have to be, you have to implement the security checks yourself. You have to implement this access control. Similarly, you have to implement authentication to make sure that you're the correct user and whatnot. And the third big thing, the big area is configuration and documentation. You need to do the right amount of threat modeling, code review, and whatnot to make sure that you can actually keep track of all those parts and make sure that the application is running correctly and is not just providing the functionality that it is intended to provide, but also restricts access to other parts that should be restricted. So a quick recap of what we have discussed. The web applications or the web is different, but also similar to other kind of issues we have looked at in the class. Daemons are long-running, complex, and exposed, and thereby offer like specific issues that we need to be aware of. Same as before, compartmentalization helps reduce attack surface, and code injection is and remains a very powerful attack vector across applications and web applications. Isolation and separation of code and data is crucial, and from the OWASP top 10, if we translate this into top 3, the issues are input parsing, authorization, and different kind of issues with configuration and documentation. I hope this gave you a little bit of an overview of the different threats in web applications or web frameworks, and allows you to connect the knowledge you have learned in this class from the other parts, the basics, mitigations, and testing towards web applications as well. This is all that I wanted to talk to you about today. Thank you for being patient on Zoom. I know this is not optimal, but I think, or I hope that I was still able to somewhat coherently explain you these slides. Let me know if there are any questions, and yeah, well, I'll be happy to answer them. Questions, please. You're very welcome. It's me who's traveling, right? So thank you for bearing with me on Zoom. So I appreciate that this actually works out. That's maybe one of the benefits of the pandemic. We have gotten more comfortable doing classes over Zoom. Even if it's not perfect, it may work for in a pitch. If there's no questions, thank you for your attention. If there are questions afterwards, do post them on Moodle, and I will be happy to answer them. Thank you very much, and see you folks around. See you folks next week. Thank you. Bye-bye.